Right, I'm going to discuss the computation of the magnetic force between two current carrying wires. If you remember, we have started with this magnetic field subject by first explaining the magnetic force, and we have said that the magnetic force is the force between two moving charges. This is the best example for the computation of such a force. And since an arbitrary shape of curved circuits are actually quite complicated mathematically, we are going to compute this force for the simplest possible circuits, simple possible current carrying wires, and these are basically infinite straight wires. Right? But of course, we know that in reality none of the wires can be infinite, but somehow I have to use the result for the magnetic field produced by an infinite wire. So as a result, I'm going to make this assumption that these wires are sufficiently long enough so that I can justify that assumption. Right? That's just a small detail, but it has to be mentioned at some point. In all problems involving magnetic fields, we know that there are cross products involved, and so as a result, the vectors, at least some of the vectors, are in the third dimension. So that's one of the features of the magnetic field that make these problems a little bit more complicated, because we have to always use this third direction. And so as a result, drawing diagrams like that would be very complicated. So as a result, to aid your visualization, I have just imagined that there's some kind of a table. There's a red table in here. So these two wires are placed on that table, right? So first, I'm going to discuss the forces and the fields from this point of view. And then at some point, I'm just going to look at the wires from this point of view. So as if I'm in here. So from that point of view, the wires actually look like a point. So that point of view was also kind of useful. So then let's go over this discussion in here. So I'm going to try to compute the force applied on the second wire. So let me also number these wires. So that's the second wire, that's the first wire. I'm going to call them as such. And so I'm going to show the force on the second wire by F2. Let me quickly write force onto in here. So force on the second wire. Let's remember the expression for this. It's the magnetic force expression on the second wire is the current I2 multiplied with the length and the cross product with the magnetic field. Right? That was the magnetic force applied on the second wire in here. There are two issues in here. One of them is the length vector. Right? I have to choose the vector like that. This is the length vector. Remember in this discussion that we are treating the currents as scalar quantities, but the lengths as vectors. Right? Do not try to express the current or think of the current as a vector. It's a scalar quantity. Currents are always scalar, but in here we are going to treat the length as vector. But of course, there should be some consistency in here. Just remember that we are expressing the currents by choosing a direction on the wire. So there is this arrow in here. So that arrow and the direction of the length should be consistent, right? Or you can say it like that. You express the current I2 along the direction pointed out by the length vector L. So they have to be consistent. So only in that case, this formula is correct vectorially, right? So that's the first thing. The second thing is the magnetic field, right? That's the expression. That's correct. But the magnetic field is actually produced by both of the wires. And when we are computing the magnetic field, we have to add them up vectorially. However, there are two difficulties in here. One of them is this. The magnetic field produced by the second wire at the location where the wire is infinity when we assume that the wire is sufficiently thin. Right? So when we compute the formula, we are going to find that it is infinite. That's one of the difficulties in here. So that's why you may not want to compute the magnetic field produced by the second wire at the place where the second wire is, right? That's the reason. Let's just say this. There's another thing in here. We have explained this when we discussed the conservation of momentum in the previous semester. We have said that the net internal forces acting within a system is equal to 0. So as a result, a system like this, a wire, the second wire in here, we can think of this as a system of particles composed of smaller pieces. The net force that the parts of that system apply to each other is equal to 0. So as a result, the different parts of this circuit perhaps produce a magnetic field which apply a magnetic force on the other parts perhaps, but when you sum them up, all of them together, they are going to be equal to 0. We basically say that a physical system cannot apply a net force on itself. So as a result, when I'm computing the magnetic force applied on the second wire, I don't need to compute the magnetic field produced by that wire itself, right? So for that reason, in here, in this formula, I'm just going to write B1 in here and just include the magnetic field due to the first wire. Let me write, this is field due to 1. Okay, so to repeat, I'm computing the force on the second wire, but for this purpose, I use the magnetic field produced by the other wires, and specifically for that problem, magnetic field produced by the first wire. The reason is the second wire cannot apply a force on itself, so as a result, when I'm computing these expressions, I just forget about the field produced by this wire when I'm computing the force applied on it. All right? So as a result, we are just going to compute this. Since I didn't define any reference frame, so as a result, we don't have these ijk unit vectors that we can use to express this in unit vector notation, which means that I need to find its direction separately and its magnitude separately, right? I need to compute both the direction and the magnitude. So let's go over this computation. So I'm going to use the yellow color for showing the magnetic fields. So first, I compute the magnetic field produced by the first wire at the place of the second one. So this is basically a field which is pointing downward. It's like that. This field is pointing downward by using the right-hand rule. So just remember the table. This B1 field is actually perpendicular to the surface of the table, and it is pointing downward. So if you would like, you can also think of that B1 is parallel to the gravity vector, right? So B1 is downward. So therefore, to find the direction of the force F2, I need to think about the cross product in here. So my thumb is along the direction of L. Index finger is downward. So middle finger therefore shows me the direction which is pointing towards the other wire. So as a result, this F2 in here is parallel to the surface of the table, and it essentially pushes the wire towards the other wire. I'm just going to say that the direction is attractive in here. The second thing is about the magnitude. Let me first write this thing down. So F2 is I2 times LB1 times sine of the angle between them. But this angle is 90 degrees. It's the angle between the length vector, this vector, and the magnetic field. They are perpendicular, obviously, so the angle between them is 90 degrees. Sine of 90 degrees is equal to 1, so therefore this is equal to the product of these three quantities. And for B1, I'm going to use the infinite line result, so that's mu0 I1 divided by 2 pi r. So we don't have much space left in here, but I'm going to repeat this calculation and discuss the magnitude later at some point. Okay. So as a result, the force is attractive, and we can also compute its magnitude. So I'm going to do the same discussion, but this time I'm going to compute the force on the first wire. Right? So I'm going to call this as F1. Right? That's force on the first wire. So as you can imagine, so that's I1 times the length across the magnetic field. This time this is the magnetic field due to, so B2 is field due to the second wire. So I'm going to do the same thing again. The direction is, let's just use the yellow color to find the magnetic field. So current on I2 is flowing like that, right? By the right-hand rule, therefore, the magnetic field at the location of I1 is like this. It's basically a vector perpendicular to the surface of the table, and it is pointing upwards. So that means this time it is opposite to the gravity, if you think in terms of the gravity. So B2 is like that. Length vector, the length is basically is in the same direction. So we just take these vectors to be the same in here. So therefore, by using the right-hand rule, we can easily see that the force is again attractive in here. So let me use this other color. So F1 is therefore a force along this direction. So it is attractive. Again, the magnitude. So that's the magnitude of the force. So F1 is therefore I1 LB2. Again, sine of 90 degrees is equal to 1. And B2 in here is equal to mu 0 I2 divided by 2 pi r. Right, you can check that these two forces are equal and the directions are opposite. All right, so I'm going to now look at this problem from this point of view. So I'm essentially in here looking at these wires from that point of view. So let's suppose that I'm far away so that I can see both wires and both wires appear like points. So from this perspective, well, this is a three-dimensional problem, all right? 3D problem. So I1 is like that and I2 is like that. Since this is a three-dimensional problem, I have to discuss this on a two-dimensional screen. And so as a result, I mean, these kind of alternative point of views are always useful because sometimes you can misunderstand some detail in there. So I'm going to repeat the discussion again, but this time about the directions. So there are these currents in here. I'm using this dot and the cross symbols. So a dot means it is basically towards us. It's a vector towards us. And a cross means into the screen. It's away from us. Right? Let's just remember this. In this problem, I have been discussing this case assuming that these two currents are positive, and I'm just going to do the discussion like that. But at some point, I'm also going to discuss the other point of view too. So let's just go ahead and then compute this. So again, let's first compute the force on the second wire, right? So for this purpose, what I do, I just compute the magnetic field produced by the first wire on the second one. So it's basically the right-hand rule. Just remember that this first wire produce magnetic field lines, which are circles, and these circles are coaxial with the wire. So the axes of these circles are the same as the wire itself. So we can also understand the direction by using our right hand, which means that there's a circle which is passing from the second wire. So that there's a circle like that, but at least on the second wire, this magnetic field is downward. So as well as it is downward at all of these locations, right? So let me erase all the other unnecessary ones and then go ahead with the discussion. The force is still, right, F2 is equal to I2 times L cross B1. So the length vector is now pointing towards us. That's the current is positive along that direction. So length cross the magnetic field is going to produce a force which is pointing towards the other one. So that's going to be F2. Right, that's for this case. Right, let's just let me erase everything in here. So I'm going to draw a new picture now. It's the same picture, but this time I'm going to discuss the force applied on the second wire. So again, the currents are approaching towards us. I'm now going to draw the magnetic field produced by this second wire at the place of the first one. Again, the magnetic field lines are circles like that. By the right-hand rule, they have the same orientation. At the location of the first wire, therefore the magnetic field is pointing upward. Right. Having said that, let me erase these details. And finally, we essentially the same as the picture on the left, except that the magnetic field is now upward. Length vector is still towards us, so therefore it is quite easy to see that for this case the corresponding force should be towards the other one. Right, so that's an attractive situation. Right, so that's one of the rules that you can easily see, that the two currents which are flowing parallel to each other, right? Two positive currents which are flowing parallel to each other, the force between the wires is attractive. So what happens if they are in the opposite direction? So this is the three-dimensional picture. So let's say that this is I2, this is positive, and this is I1. So the wires are parallel, but the positive currents are flowing in opposite directions. So in this two-dimensional picture, we have a situation like that. I'm looking from this point of view, right? I'm here. So therefore, I2 is towards us, but I1 is into the screen. Right? I'm going to discuss it on the same picture now. So you can see that magnetic field produced by I1 is, again, circles, but this time the direction is like that. Which means at the location of the second wire, the magnetic field B1 is pointing upwards. Right? So therefore, the force on the second wire is, length vector is towards us, B is upward, so that means the force is in the other direction. So this F2 is therefore is positive in the leftward direction. So I'm going to continue the discussion on the, let me draw a new picture in here. Right, it's the same physical system. Again, I1 is into the screen and I2 is out of the screen. But this time I'm going to compute the force on the first wire. Let's remember the magnetic field produced by the second wire. So the field lines are like that. All right. And so therefore, the magnetic field produced at the location of I1 is upward. So the magnetic field is upward now, which means the magnetic force acting on the first wire, the length vector is now pointing into the screen. B2 is upward, so by the right-hand rule, therefore the corresponding force would be in the rightward direction. So this is the direction of F1. All right, so as a result, we get the same picture again. So as a result, if the currents are anti-parallel to each other, then the magnetic force is opposite. So if you think of these wires as like the points in this two-dimensional picture from this point of view where we actually see the wires as points, the repulsive and attractiveness of the force is just opposite to the electric case. So if you remember, for the electric charges, the like charges repel and unlike charges attract each other. Now it appears that it is the opposite in here. So as a result, for example, if I have a third one in here, so let me erase some details in here, right? Forget about the values as well. So as a result, if I have a third current carrying wire in here, so these two current carrying wires are like charges. So in those cases, these two are going to attract each other, and they are going to repel this one in here. So as a result, the unlike current is going to be pushed outward, and of course this is also going to push these charges in the outward direction, but they are going to attract each other. All right, it's just an opposite situation for the current carrying wires. All right, there's no significance in here. So let me also discuss the magnitude. So this time I'm going to say something about the magnitude. So we know that the forces are equal and opposite. By Newton's third law, they have to be equal and opposite. And the magnitude is given as mu0 divided by 2 pi multiplied with the currents divided by r and multiplied with the length. One of the details in here is that the force is proportional to the length. Right? That's reasonable physically, obviously. If you have a longer wire, of course, the same force is going to act on a longer version, so therefore the net force would be bigger, obviously. So, but people usually then, instead of discussing forces, they discuss the force per unit length. So as a result, it's the force per unit length which people usually compute. It's I1, I2 divided by R. Right, let's just compute for the special case where, let's think of these as typical values. So if the currents are about 1 amperes and the distance is 1 meters, in which case the force per unit length acting on any of the wires is equal to mu0 was equal to 4 pi times 10 to the minus 7 divided by 2 pi in here, and these values are all equal to 1. So as a result, we get a value which is 2 times 10 to the minus 7 newtons per meter. So the unit is newtons per meter. Okay, so as a result, the first comment is that this is a very small force. So think of it as 1 ampere is a typical large current. In smaller electronic circuits, the amount of the current is even much smaller than these. Distance, well, we can meet smaller distances perhaps, but 1 meter is a typical distance. So you can kind of see that this, at least for the, as a force between wires, this is very small indeed. So probably we won't notice it, but the experimental devices can measure this force. So then we come to the second topic. So up until the last year, this was actually a basis of the definition of the ampere unit. So just remember that we have to define our units as well. So we have to describe how they are defined, and then we use this definition for all other cases. So up until the May of 2019, the last year, they were defining the ampere as the unit in such a way that when these 2 ampere currents flow in 2 parallel wires, which is separated by a distance of 1 meters, right? In that case, they would produce a force which is of exactly of that magnitude, right? So in a way, they define the ampere unit such that the the permeability quantity in here, this is mu 0 in here, is exactly equal to 4 pi times 10 to the minus 7. And the unit is, I believe it is, I need to look at this. So this Newton per meter, so therefore it's Newton per ampere squared, right? They have been defining it like that. But last year there was a change adopted by everybody. So instead of defining units like that, they have defined some certain exact values for some fundamental constants. Speed of light has been taken to be constant for a long time. Now they are taking the Planck constant as a constant quantity. You are going to see about the Planck constant later. And the charge of the proton, charge of the electron, they also define it. So once we define these, once we define the Coulomb unit in such a way that the electron's charge has this precise value, in that case, of course, the other quantities have to be measured. So as a result, since the last year, the permeability of the vacuum, mu 0 quantity, does not have the exact value given by this thing now. This is now approximate, so people are now measuring this quantity, and I believe that they also have obtained the deviations of mu 0 from that given value in here. In any case, this is one of the things that has just been changed recently. But usually this topic of how the units are defined and how people measure these constants of nature in a highly precise way, this is usually a complicated topic, so it just involves some advanced use of some phenomena.